14.8 is on what's called Lagrange multipliers. So we apply this method to find extrema of a function. So suppose you had something like this, f of xy equal to xy. But your values xy, your points, are restricted to, say, this curve, some curve. Okay, so that is not a region in this case. That's an ellipse. And then what's the maximum or minimum values of xy? So here's the theorem. The theorem doesn't really tell us a whole lot. It's really the corollary and kind of procedure of how we use it. But let's look at the theorem, what it says. So this is Lagrange multiplier theorem. It says suppose f and g are functions of two variables. With continuous first partials. And the gradient of g does not equal the zero vector in a region. So whatever specified region it is, basically, in a region R that contains like the curve, right, in the xy plane. Okay, if f has extremum, so there are extreme values of the function. So if f has extremum, f of x naught, y naught, subject to that constraint, so subject to the constraint, g of xy equal to c, or you could even just say equal to 0 and just bring over the constant, but it doesn't really matter where that constant is. Then there exists a lambda, and I'm sure they use lambda for the Lagrange thing, in R, in the reals, such that the gradient of f of x naught, y naught is equal to lambda times the gradient of g of x naught, y naught. So that's the multiplier aspect of it. This is a constant multiplier of f and g. So in other words, basically, whatever that gradient is, it's just a multiplier by it. It's like pointing in the same direction. So it's basically going on, and I'll show you the proof later, but you have, so like suppose you had that curve, and then the gradients are going to be perpendicular, right? So you basically, let's see, basically going like this, and then the gradient of g, well, so basically f's in the same direction. So the gradient of f is going in that same direction. I mean, it could be negative, actually, for lambda. But that in itself doesn't really help us to figure out this theorem. I'm going to erase that because I'll show you better stuff later. All right, so this form is partial fx partial fy equal to lambda times partial gx gy. And you can extend this to more than two variables if you want. So how do we use that? There's really the question. This is the corollary. That's what we really apply, is the corollary. So this is corollary slash procedure, basically. Okay, so I'm not going to state it out all the way again. Let F and G satisfy the hypothesis. So satisfy the hypothesis above. Good enough for us today. And then what you do is you solve the system. Okay, solve the system. You basically equate components. So that's why I have those highlighted. So basically, you set this equal to g of x, and then you set f of y equal to g of y. So it looks like this. Partial fx of xy equal to lambda times partial gx of xy. Then here's your other equation, partial fy of xy equal to lambda partial gy of xy. But you can't forget, you must also satisfy the constraint that g of xy equal to 0. So often you get, a couple of solutions to this system, but those ordered pairs must also satisfy that constraint. All right, so then what you do is this. The solutions will be in the form you'll have a list of them, x1, y1, and then lambda 1. And you keep going. I'll just do it like that. I mean, it'll stop. Well, I could say it's k, I guess. So then you'll have x k, y k, lambda k, like that. So you discard the lambdas. Okay, so we discard lambda i's and use the points x1, y1, etc. to xk, yk. Then we determine if each point is a maximum, minimum, or neither. So you just plug it in and see what it is. Then we determine if each point is a max, min, or neither. So if you have 3 different points, this one would be a max, this one would be a min, and this would be neither. That kind of thing. Okay, so you list them out, make a chart, biggest one, max, smallest one, min. Could have, multiple max, multiple min, but it's there. Basically, this is absolute max and min on a constraint. All right. Where was I at? All right, let's look at an example. Let's go to the next page. I was just citing that. Okay, so let's take a look at this. Okay, so find extrema, find the extrema of f of xy equal to xy, so same one as above, if xy is restricted to, and it's the same thing, to the ellipse, because I tell you what it is now. Of course, we all know that. So it's restricted to the ellipse 4x squared plus y squared equal to 4. All right, so we can get started by dividing by the 4. So you have x squared plus y squared over 4 equal to 1. Although I guess it really wouldn't matter. But that's that. I just wanted to show you that that's the ellipse. And it's basically going this way because the longer side is 4. We're going to delete that and do it again later. Okay, so what you do, and this is one of those things where I'll tell you to use Lagrange multipliers. So I'll say apply Lagrange multipliers. Otherwise, you can do this just using other techniques. You can just do the first partials test and then apply it to that constraint and that kind of thing. So we're going to let g of xy equal 4x squared plus y squared equal to 4, and that's our c. And you can see when you do the gradient of that anyway, those constants are going to disappear regardless. Okay, so then we do the gradient calculations. You're going to do partial fx y. So if you were to like have to memorize something or write something down, this is what you would write down. You write down that these gradients have to equal each other. That's what you write down, and then the constraint. So you'd write that down, and then you'd write down the constraint, which is the 4x squared plus y squared equal to 4. And you're basically solving that system. So this is really what you would be doing. So the other way to write that is to go ahead and do how I have it above, partial fx fy, because that's the gradient, equal to lambda times gx partial gy. And then go ahead and do that. I'll just give you some room so you can see. So partial fx is just going to be fx, what am I at? Where's f? Oh, okay. I was looking at the wrong thing. I'm like, that can't be right. Okay, looking at that, partial fx is just y. Partial fy is just x. Then you say lambda times gx. So your gx is just 8x. And your gy is just 2y. Okay, so then we also know that this is equal to 8 lambda x and 2 lambda y. So now you're equating those components. You're going to set 8 lambda x equal to y, and you're going to set x equal to 2 lambda y. So your system is y equal to 8 lambda x, and x is equal to 2 lambda y. Okay, and then you also have 4x squared plus y squared equal to 4. So this, when you solve this, one of the key things is never, so let me write this down. See if I can, it shows up. So never divide out a factor. Like a variable factor. Maybe we'll put out a variable factor. Okay, that's kind of one of the keys to solving these, because it looks kind of like, how would you do that? You know, it looks kind of simple, but you do get some interesting solutions to this. When you're looking at this too, you can eliminate some possibilities. So clearly, if x is 0, y is 0. So what about 0, 0? That's always a good one to check. So I'll write it down. What about 0, 0? Could that work? Well, it satisfies both of these, right? Check that, right? It satisfies both of those, but does it satisfy the constraint? So 0 plus 0 is not equal to 4. So no, right? So it does not work. So you can't use 0, 0 in this case. All right, so then what you can do is basically substitute. So we're going to take, how do I do this? We're going to take y. This y is 8 lambda x, and we can put it right here. So you get this, and there's different ways to do it, but I'll just show you what I have. So I have x is equal to 2 times 8 lambda x times lambda, which is 16x lambda squared. All right, so now I'm going to take both sides and rewrite that as x minus 16x lambda squared equal to 0. And then I'll keep going. And so I factor out, that's an if and only if, factor out the x. I have 1 minus 16 lambda squared equal to 0. So that's true if x is 0 or lambda is plus or minus 1/4. And we already established we're going to throw out or omit the 0 case because it doesn't satisfy the constraint. All right, so I don't think I made a note of that in my notes, but okay, so now we can continue to solve. If lambda is plus or minus 1/4, then what do we get? Then y is equal to 8 lambda x, which is 8 times plus or minus 1/4 times x. And let's just move this down. Which is equal to plus or minus 2x. All right, so now substitute for y. In the constraint. So we have 4x squared plus y squared is equal to 4, which is the constraint. So we get 4x squared, because that's what y is equal to, right? Y is equal to this, so we're going to plug that in right there. Solve for x. It's like we need one more equation to solve for x. This isn't linear. It's not. So you're not like solving a system of linear equations. This is a nonlinear, overdetermined system. Usually is what you call it. You got to be creative about it. Just the hardest part is solving the system, basically. Anyway, let's continue. So you get plus or minus 2x squared. So the plus or minus doesn't matter. So it's 4, and then you just continue to solve that. You get 4x squared plus 4x squared equal to 4. If and only if. You can see what you're going to get there. 8x squared is equal to 4. Or x squared is a half. If and only if x is equal to plus or minus 1 over root 2. Or if you'd like, you can write that as root 2 over 2. I don't really care about stuff like that, but just sometimes the book has that. All right, so now, okay, and we can solve for x now. For y, I'm sorry, solve for y now. All right, so solving for y, we have, where's y? So y is just plus or minus 2x. So when you do that, you get y is equal to plus or minus 2x. So it's plus or minus root 2. All right, so they're all independent of each other. So there's, so you have critical points now, and there's 4 possible. So you have plus or minus root 2 over 2 and plus or minus root 2. So there's 4 possibilities to look at, to test, right? So you put down, you got to be a little bit organized sometimes about this. So we're going to do root 2 over 2. So we're doing each of these points. So we're going to do root 2 over 2. And so positive, positive. Then we're going to do positive, negative. Then we're going to do negative, positive. And then we're going to do negative, negative. And then you just substitute in for your function, which is just x times y. And you evaluate, you get 1, you get negative 1, negative 1, and positive 1. So those are on your constraint. When you do that product, the conclusion then is that's a maximum value. This would be the minimum. This would be another minimum. And this would be a maximum. So what you're getting, you have some function in the xyz plane, but in the xy plane, you have this ellipsoid, or it's actually an ellipse, not an ellipsoid. So you have an ellipse that's supposed to be about like that. I can draw this pretty close, pretty close. And right at root 2 over 2, so basically, right about here, and here, and then negative, and here, the positive case, that's your max. Negative, negative is max. And then these are your minimum values. So that's a min, and this is a min. That's what you end up getting. You can graph that as well. and see what the xy looks like. It's not really critical at this stage to do that. We won't be really doing that. But on this ellipse, you have a function above here doing something. And then with the values restricted to the xy values restricted to this, that's when you get your min and max. So it probably is like folded somehow, and it goes minus down here and goes positive on positive, positive, negative, negative. This is what's going on. So from here, we just applied that theorem a couple more times. I have 2 more, and I'll do the proof eventually for you. Okay, we'll call it a night on this one.